Hey guys, so in this video we're going to be going through Laplace or cofactor expansions for determinants. So for this video I'm going to assume that you know how to calculate the determinant of a standard 2 by 2 matrix. Say if I said A was this matrix here, A, B, C, D, then its determinant would be AD minus BC, where of course A, B, C, and D are all real numbers. So now what if your book asked you to calculate the determinant of something higher, like let's say B equals this matrix here, A, B, C. Now how would you calculate the determinant of B? So where of course A, B, C, D, E, F, G, H, I are all just real inputs, they're all real numbers. How would you calculate the determinant of B? So that's what we're going to be covering in today's video. So let's just go through the formula real quick. Now, the formula for so we're going to start off with cofactor expansion, and then we're going to link it to determinants. So basically, the formula for a Laplace or a cofactor expansion is Cij equals -1 to the I plus j multiplied by the determinant of your new matrix, which is Aij. This is a matrix that's contained within your larger matrix. I'll show you what that means in a moment, but this is your equation for cofactor expansion, where I is the ith row and j is the j column. So that's that. Now let's really just get into an example, because just having this formula like written here is really of no use without an example. So consider the following matrix, right? A equals 1, 0, actually 0, 0, 1, 1, 0, 1, and 2, 1, 2. Now, this is a square matrix. Remember, you can only compute determinants for square matrices. So that's that. And so we use Laplace or cofactor expansions to calculate the determinants of bigger matrices like these, because the rule that I stated earlier can't really apply to this kind of matrix. We'll see that like how it will, but like if we just try to apply it in here, it won't work. And if we had bigger matrices, say in R4 or R5, then it would get really tricky. So we use Laplace or cofactor expansion to help us compute determinants. So let's say compute the determinant of A using cofactor expansion. Right? So let's go ahead and do that. Now, first thing we want to know, like find out, right, is okay, so let's like put back in the formula back into use, right? So the whole kind of intuition behind cofactors expansion is we either lock the row or we lock the column, i.e. we just do it. We choose one particular row, say row 1, row 2, or row 3, and we just lock. So we stay in that row, but then we change columns. So we move from this column to this column to this column, or we can do it the other way, vice versa. So for this video, what I'm going to be doing is I'm going to be locking the row. So I'm going to stay in row 1, but I'm going to be shifting from column 1 to column 2 to column 3. So let's go ahead and write down our equation. But now that I know that I'm always going to be in the first row, I can just write C1 comma J, or my jth column is just going to be -1 to the 1 plus j times the determinant of A1j. So now the next step is, what we're going to do is, what we kind of do is, now let's like imagine we block out this entire row, this entire column and this entire row. So first bit is that, right? So this means that I'm blocking off my entire first row and my first column. So that just means my j is 1. This is for j equals 1, and of course the I is always going to be 1. So let's compute the cofactor expansion of this one. So this will become 1, 1, which is negative 1 to the 1 plus 1 times the determinant of a 1, 1. But what is this? What is this, you may ask? Notice that we have this new matrix here that is actually 2 by 2. So this matrix here is what goes in here. This is the remaining 2 by 2 matrix when we eliminate the first row and the first column. So the formula will look like this. This will just become negative 1 to the power of 2 times the determinant of the matrix is going to be 0, 1, 1, 2. And let's go ahead and compute that. So that's just going to be the cofactor of 1, 1 is just going to be, this will go to 1, and so the determinant of this is just going to be 0 times 2, which is 0 minus 1, is just going to be negative 1. Cool, now let's go ahead and compute the cofactor of the same row, but this time the second column. How could we do that? This time, I'm going to block off my entire first row here, but then I'm also going to block off the second column. So now I'm left with this, and this. So that's going to be my new matrix for 2 by 2. So let's go ahead and compute C of 1, comma 2. Remember, your first row, second column. And so that's going to be negative 1 to the power of 1 plus 2 times the determinant of your new matrix is going to be 0, 1, 1, 2. And this is just going to mean the negative determinant of 0, 1, 1, 2. And computing that determinant, we're going to get 0, minus 1, and negative, negative 1 leaves positive 1. So the cofactor of 1, 2 is just going to be 1. Similarly now, we can go ahead and compute the cofactor of the third column with the first row. So let's go ahead and do that. So C1, 3, and go ahead and try that for yourself actually. So you can pause the video, block off that, and we're left with these 4 numbers here. So negative 1 to the 1 plus 3, or that's just going to become 4, or that's just similarly going to become positive 1. And so this is just going to be the determinant of 0, 0, 1, 1. And computing that, we get the cofactor of 1, 3 is to be 0, 0. Now here comes the determinant bit. We've computed all 3 cofactors, right? But now we have to compute the determinant, right? So in order to compute the determinant, we have another formula here. Now, basically, in our case, what we're doing is we're holding the ith row constant, and the jth row, and sorry, the jth column, we're changing that. So we can express the determinant of A as a sum. So the sum looks like this. The sum from j equals 1 through to n, where n is like basically how big the matrix is, because it's always a square matrix. So for example, this one will be all the way to 3 for j equals 1 to j equals 3. And that will just be the entry in your ith row and your jth column in your original matrix A, multiplied by the cofactor expansion that we just computed of your same ith row and jth column. And that's how you calculate the determinant. Now, it seems like an intimidating formula, but I'll show you like how we can break it down. Or similarly, once again, if you want to just if you prefer the other way, where you hold the jth column constant and you want to switch to ith row, then you can just swap that for I pretty much, and then you just sum over that. So let's go ahead and actually use this formula. So what this formula is stating now is I'm summing this from, for our particular case, n equals 3. So we're going to sum till 3. So this means I'm going to take my I is already a constant. It's 1, right? So I'm just going to write 1 and 1. So what this means is it's going to be the entry in A at 1, 1 times the cofactor of 1, 1 plus the entry of A in 1, 2 times the cofactor of 1, 2 plus the entry in 1, 1, 3 times the cofactor of 1, 3. And that's your determinant. So let's go ahead and go back to our original matrix. So we have this matrix here. What was that number? I think it was 2. And so in the first row, in the first column, the first row, first column, our entry is 0. Second one is 1. And your third one is 2. So what that means is that this will be 0 times the cofactor of 1, 1 plus 1 times the cofactor of 1, 2 plus 2 times the cofactor of 1, 3. And so if we just substitute in 0 times, no matter whatever the cofactor of 1, 1 was, will be 0. Cofactor of 1, 2 was 1, as we can see. So plus 1 times 1, and this was actually negative 1, plus 2 bracket 0, and these terms are just 0, so we get that the determinant of A is just 1. That is the determinant of this 3 by 3 matrix here. Cool, so we got that done there. Now I'm just going to go through one more practice example, and that should hopefully really summarize it really well for you guys. So let me just go ahead and clear this out. Now I'll write the formulas once again, but so basically the determinant of a particular matrix A is just going to be the sum from J equals 1 to whatever the dimension, like if it's a 3 by 3, 4 by 4, 2 by 2 matrix, whatever, that's what the n is. It's just going to be the sum of the entry of I at your ith row and your jth column entry multiplied by your relevant cofactor expansion that you computed at I and j. So these are your two formulas that you're going to need. And so what if I gave you the matrix that looks like this? A equals A, B, C, D, E, F. So how would you compute the determinant? So let's go ahead and do this, because if I can generalize it, okay, just to make it clear though, A, B, C, D, E, F, G, H, I, these are all elements of the real numbers. So these are all just real inputs, basically. How would we compute the determinant of A using cofactor expansion? Now this kind of will be a general formula, so you can by the end of this you'd be able to basically punch in the numbers and calculate any determinant for a 3 by 3 matrix of this form. So let's go ahead and start by computing the relevant cofactor expansions. So we're going to do the same method. So cofactor of 1, 1, I'm going to block out this column and this row, and that's just going to leave this here. So it's just going to be negative 1 to the 1 plus 1 times the determinant of the matrix EFHI, and then that's just going to be equal to the determinant of that, which we know is just going to be, so this is just going to go to 1, and so it's going to go to EI, or I'm going to say IE minus HF. So your cofactor of 1, 1 is this. Cool. Let's go ahead and calculate the cofactor of the next one here. So your next cofactor, imagine you block that out and block that out. So next one is going to be the cofactor of 1, 2, and that's just going to be negative 1 to the 1 plus 2, or negative 1 to the cube, which is negative 1. And we're just going to write negative determinant of the matrix DFGI. And let's go ahead and compute that. So we're going to get negative, and then ID minus FG, or that's just the same as saying FG minus ID. That's your relevant cofactor expansion of 1, 2. Cool. Now we got only one more left to do. Let's go ahead and compute that one there too. So once again, we block out that entire row, and we're just going to block out that column there. And so your cofactor expansion of 1, 3 is just going to be negative 1 to the power of 4 times the determinant of the matrix DEGH. And then we go ahead and simplify that. So this is just going to go to 1, and the determinant of this is just going to be DH minus GE. So that's your cofactor of 1, 3. Cool, we got that there. We got our 3 cofactors. And now let's just go ahead and punch everything into this determinant formula that we have up here. So I'm going to do that in a different color. Just switch over to blue. So then, once again, we know that formula for determinant of A. So it's just going, your determinant of A is just going to be the first entry, the entry in 1, 1, which is A. So that's A. It's multiplied by this C11, which is IE minus HF, plus, because it's a sum, plus your next entry, which is B, and then 1, 2 is just FG minus ID, plus C bracket DH minus GE. And so if you have any 3 by 3 matrix, the determinant of that particular matrix will be this, where of course all of the variables in here are real numbers. And so yeah, that's a pretty simple, quick introduction to Laplace or cofactor expansion.